The practice of running transformer primary and secondary conductors in the same raceway is sometimes seen in electrical installations. While specific code references may not directly address this configuration, it is generally considered acceptable under certain conditions. The key concern is ensuring the safe separation and support of the conductors to prevent the primary conductors from arcing over to the secondary conductors. One acceptable method is to provide adequate physical separation between the primary and secondary conductors within the raceway. This can be achieved by using cable ties or other securing devices to maintain a clear space between the conductors. It is crucial to prevent any contact or close proximity that could lead to arcing in the event of installation failure or damage. An alternative approach involves running the primary conductors in a separate conduit that is securely fastened alongside the conduit containing the secondary conductors. This method provides a physical barrier between the two sets of conductors, minimizing the risk of arcing. The separate conduits must be properly supported and bonded to ensure electrical safety. Another method involves using a special conduit body that incorporates separate compartments for the primary and secondary conductors. These conduit bodies are designed to maintain physical separation between the conductors, providing an additional layer of safety. They are typically used in situations where space is limited or where a higher level of protection is desired. Regardless of the method used, it is essential to ensure that the conductors are properly sized and insulated for the voltage and current they will carry. The conductors must also be protected from physical damage and environmental factors such as moisture and corrosion. All electrical work must be performed by qualified personnel in accordance with applicable electrical codes and standards. When considering running transformer primary and secondary conductors in the same raceway, it is important to carefully assess the specific installation conditions and potential risks. Factors to consider include the voltage and current levels, the size and type of conductors, the type of raceway, and the environmental conditions. It is also important to consult with local electrical inspectors or engineers to ensure that the installation meets all applicable requirements. Proper grounding and bonding are essential for electrical safety. The transformer and all associated equipment must be properly grounded to provide a low impedance path for fault currents. Bonding is used to connect all metal parts of the electrical system to ensure that they are at the same electrical potential. This helps to prevent electrical shock hazards and minimize the risk of fire. Overcurrent protection is another important safety consideration. Fuses or circuit breakers must be installed to protect the transformer and conductors from overloads and short circuits. The overcurrent protection devices must be sized appropriately for the transformer and conductor ampacity. Regular inspections and maintenance are essential to ensure the continued safe operation of the electrical system. Inspections should be performed to check for any signs of damage, wear, or corrosion. Maintenance should include cleaning, tightening connections, and testing protective devices. Any problems that are identified during inspections or maintenance should be corrected promptly. When working with electrical equipment, it is important to follow all safety precautions. Always to energize the equipment before working on it. Use appropriate personal protective equipment, such as gloves and safety glasses. Be aware of the potential hazards and take steps to mitigate them. If you are not qualified to perform electrical work, do not attempt to do so. Hire a qualified electrician to perform the work safely and correctly. Remember that electricity can be dangerous, and it is important to take all necessary precautions to protect yourself and others. In summary, while not explicitly prohibited by code, running transformer primary and secondary conductors in the same raceway requires careful consideration and implementation. Ensuring adequate physical separation, proper conductor support, and adherence to all applicable electrical codes are paramount for safe and reliable operation. It's always best practice to consult with qualified electrical professionals to guarantee compliance and safety in such installations. When dealing with electrical installations, certain calculations are essential for ensuring safety and compliance. One crucial calculation involves determining the appropriate conductor size for the primary and secondary windings of a transformer. The conductor size must be adequate to carry the full load current without overheating, which could lead to insulation failure and potentially a fire. The National Electrical Code, or NEC, provides tables, such as NEC Table 310.16, that specify the allowable ampacities for various conductor types and sizes based on their insulation temperature rating and the ambient temperature. To determine the required conductor size, one must first calculate the full load current for both the primary and secondary windings. The formula for calculating the full load current in a single-phase transformer is volt-amps divided by volts. For a three-phase transformer, the formula is volt-amps divided by volts multiplied by the square root of 3, which is approximately 1.732. Once the full load current is determined, the appropriate conductor size can be selected from NEC Table 310.16, ensuring that the conductor's ampacity is equal to or greater than the calculated full load current. It is also important to consider any derating factors that may apply. Derating factors are adjustments to the conductor's ampacity to account for factors such as high ambient temperatures, multiple conductors in a raceway, or continuous loading. If the ambient temperature is higher than the temperature rating of the conductor's insulation, the ampacity must be derated accordingly. NEC Table 310.15 provides derating factors for various ambient temperatures. If there are more than 3 current-carrying conductors in a raceway, the ampacity must also be derated. NEC Table 310.15 provides derating factors for different numbers of conductors in a raceway. If the load is considered to be continuous, which means that it operates for 3 hours or more at a time, the conductor's ampacity must be derated to 80% of its rated value. This is because continuous loads generate more heat, which can cause the conductor to overheat if it is not properly derated. Another important calculation involves determining the appropriate size for the overcurrent protection devices, such as fuses or circuit breakers, that protect the transformer and conductors from overloads and short circuits. The NEC specifies the maximum allowable overcurrent protection for transformers in NEC section 450.3. For transformers rated 600 volts or less, the primary overcurrent protection is typically limited to 125% of the transformer's primary current rating. The secondary overcurrent protection is typically limited to 125% of the transformer's secondary current rating. However, there are exceptions to these rules, depending on the transformer's impedance and the type of overcurrent protection device used. It is important to consult NEC section 450.3 to determine the specific overcurrent protection requirements for a particular transformer. In addition to conductor sizing and overcurrent protection, grounding and bonding are also essential for electrical safety. Grounding provides a low impedance path for fault currents, which helps to prevent electrical shock hazards and minimize the risk of fire. Bonding connects all metal parts of the electrical system to ensure that they are at the same electrical potential, which also helps to prevent electrical shock hazards. The NEC specifies the grounding and bonding requirements in NEC Article 250. The grounding electrode system must be properly installed and connected to the building's grounding electrode system. All metal enclosures, raceways, and equipment must be properly bonded to the grounding electrode system. In summary, performing accurate electrical calculations is essential for ensuring the safety and compliance of electrical installations. Conductor sizing, overcurrent protection, grounding, and bonding are all critical aspects of electrical safety. It is important to consult the NEC and other applicable standards to ensure that all calculations are performed correctly and that the electrical system is installed in accordance with all applicable requirements. Remember, always consult with a qualified electrical professional for any electrical work to ensure safety and compliance. When dealing with transformers, understanding the different types of transformers and their applications is essential. Transformers are broadly classified into 2 main types: core type and shell type. Core type transformers have the primary and secondary windings wound around 2 separate limbs of a magnetic core, while shell type transformers have both windings wound around the center limb of a magnetic core. Shell-type transformers generally offer better mechanical strength and are more suitable for high-voltage applications. Transformers can also be classified based on their voltage transformation ratio. Step-up transformers increase the voltage from the primary to the secondary winding, while step-down transformers decrease the voltage. Step-up transformers are commonly used in power transmission systems to increase the voltage for long-distance transmission, reducing losses. Step-down transformers are used at substations and distribution points to reduce the voltage for local distribution to homes and businesses. Autotransformers are another type of transformer that has only one winding, which is used as both the primary and secondary winding. Autotransformers are smaller and lighter than conventional transformers of the same rating, but they do not provide electrical isolation between the primary and secondary circuits. They are commonly used in applications where voltage regulation is required, such as in motor starters and lighting dimmers. Isolation transformers are used to provide electrical isolation between the primary and secondary circuits. They have separate primary and secondary windings that are not electrically connected. Isolation transformers are used in sensitive electronic equipment and medical devices to protect against electrical noise and ground loops. Instrument transformers are used to measure high voltages and currents in power systems. They include current transformers or CT and potential transformers or PT, also known as voltage transformers or VT. CT step down the current to a safe level for measurement, while PT step down the voltage. They are used in metering, protection, and control applications. Dry-type transformers are cooled by natural air convection or forced air cooling, while liquid-filled transformers are cooled by oil or other insulating liquids. Dry-type transformers are typically used indoors, while liquid-filled transformers are used outdoors or in substations. Liquid-filled transformers are more efficient at dissipating heat than dry-type transformers, making them suitable for high-power applications. Three-phase transformers are used in three-phase power systems to transform voltages and currents. They can be connected in various configurations such as delta-delta, delta-Y, Y-delta, and Y-Y. The choice of connection depends on the application and the desired voltage and current characteristics. Rectifier transformers are used to supply power to rectifiers, which convert alternating current or AC to direct current or DC. They are designed to handle the harmonic currents generated by rectifiers. Grounding transformers are used to create a neutral point in a three-phase system, which is necessary for grounding purposes. They are typically connected in a zigzag or Y-delta configuration. In summary, understanding the different types of transformers and their applications is crucial for selecting the appropriate transformer for a particular application. Factors to consider include the voltage transformation ratio, the isolation requirements, the cooling method, and the type of power system. Always consult with a qualified electrical professional for any electrical work to ensure safety and compliance. When working with electrical installations, it is important to understand the concept of impedance and its role in circuit protection. Impedance is the total opposition to the flow of alternating current or AC in a circuit. It is similar to resistance in a direct current or DC circuit, but it also includes the effects of inductance and capacitance. Impedance is measured in ohms and is represented by the symbol Z. Impedance is a complex quantity that has both a magnitude and a phase angle. The magnitude of the impedance represents the total opposition to the flow of current, while the phase angle represents the phase shift between the voltage and current. In a purely resistive circuit, the impedance is equal to the resistance, and the phase angle is 0 degrees. In a purely inductive circuit, the impedance is equal to the inductive reactance, and the phase angle is 90 degrees. In a purely capacitive circuit, the impedance is equal to the capacitive reactance, and the phase angle is minus 90 degrees. In a circuit with both resistance and reactance, the impedance is calculated using the following formula: Z equals the square root of R squared plus X squared, where R is the resistance and X is the reactance. The reactance is the difference between the inductive reactance and the capacitive reactance. Impedance plays a crucial role in circuit protection because it limits the amount of current that can flow in a circuit. When a fault occurs, such as a short circuit, the impedance of the circuit decreases significantly, which causes a large increase in current. This high current can damage equipment and cause a fire. Overcurrent protection devices, such as fuses and circuit breakers, are designed to interrupt the flow of current when it exceeds a certain level. The impedance of the circuit determines the magnitude of the fault current, which in turn determines the required interrupting rating of the overcurrent protection devices. The interrupting rating is the maximum amount of current that the device can safely interrupt without being damaged. It is important to select overcurrent protection devices with an interrupting rating that is equal to or greater than the available fault current at the point of installation. The available fault current is the maximum amount of current that can flow in the circuit under fault conditions. It is calculated based on the impedance of the source, the conductors, and the equipment in the circuit. Short circuit studies are typically performed to determine the available fault current at various points in the electrical system. These studies involve calculating the impedance of the circuit and using this information to determine the fault current. The results of the short circuit studies are used to select the appropriate overcurrent protection devices and to ensure that the electrical system is properly coordinated. Coordination refers to the selection and setting of overcurrent protection devices so that they operate in a specific sequence to isolate a fault. The goal of coordination is to minimize the extent of the outage and to prevent unnecessary tripping of upstream devices. Impedance also plays a role in voltage drop. Voltage drop is the decrease in voltage along a conductor due to the impedance of the conductor. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the electrical system. The NEC specifies the maximum allowable voltage drop for various types of circuits. The voltage drop is calculated based on the impedance of the conductor, the length of the conductor, and the current flowing through the conductor. In summary, impedance is a fundamental concept in electrical engineering that plays a crucial role in circuit protection, voltage drop, and system coordination. Understanding impedance and its effects is essential for designing and installing safe and reliable electrical systems. Always consult with a qualified electrical professional for any electrical work to ensure safety and compliance.